All right. So you do not need to know too much about bridge or whist for this, although if people want to learn, I am happy to teach. I think the second time I ever taught probability here, I taught some students in my probability class how to play bridge. It was the first time I ever publicly cursed out one of my students because of a very bad card playing they did. It was so bad it actually drove me to profanity. Okay, and I will talk about that, but not on the record. All right, so I'm trying to get the camera to move and follow. All right, so the way it works is the following. In bridge, you have two teams of two. Each team has two players. And a special suit is often trump, and you often bid to see which is going to be that special trump suit. And so let's pretend hearts is the trump suit. And so what I want to do now is I want to calculate what's the probability that the other team, the other two people, have a certain distribution of their cards. So I will assume that I know my team has 8 hearts. There are 13 hearts total. 13 minus 8, if I have done the calculation correct, is 5. Good. Okay. So there's 5 hearts remaining. I'm going to assume it's really bad if all 5 hearts end up in one of my opponent's hands. As long as that doesn't happen, I'm going to assume I'm going to be in great shape. But if I have this disastrous trump split where all 5 missing trumps are in one hand, I'm in trouble. What is the probability that this happens? So I want to know what's the probability all of the hearts are in one of the 2 missing hands of 13. Okay, here are 3 different arguments. The first argument, the second, and the third argument, they all start with a factor of 2 because there's 2 ways it could happen. Either my first opponent has all 5 or my second opponent has all 5. I don't have to worry about both events happening because there are only 5 missing hearts. Both of them can't have the 5 hearts. And for the first person, I said, well, look, I choose which of the 2 players has the 5 hearts. That's 2, or really 2 choose 1. He has 13 cards that I have to assign. I give him the 5 hearts, 5 choose 5. There are now 26 minus 5, or 21 cards remaining. And I have to have a hand of 13 cards, so I do 13 minus 5, or 8 of those cards. This is the number of ways to give that person 5 hearts and then another 8 cards. I divide by the number of ways to give that person 13 cards, and that fraction will be the percent of time the first person has all 5 hearts. I then multiply by 2. That's the probability one of the 2. And when you do the calculation, you get about 3.913%. Second argument. All right, again, factor of 2. And now let's look at the cards one at a time. And so what I will do is, in the interest of time, I will just pull out 5 hearts. I don't really care which 5 hearts it is. I should have prepared this, so I'm just grabbing the first ones I can. So let's say it's the 3 of hearts, the 4 of hearts, the 6 of hearts, the 8 of hearts, and the 10 of hearts. And as I'm dealing the cards, I look at, who gets this card or not. Does one player get all of them? And so for the first card, there are 13 slots it can go to for player 1. There are 26 slots total, so the probability the first person gets this heart is 13 out of 26. Now let's look at the next heart. I have 12 slots remaining for that first person, so the probability that they get the next heart is 12 out of 25. For the next one, there's 24 slots remaining, 11 out of 24, 10 out of 23, and then 9 out of 22. And at the end of the day, when the dust settles, you get 3.913%. Final argument is the following. We are over-analyzing this enormously. We don't need to know all this stuff. Look, what's the probability one of the players gets the 3 of hearts? What's the probability the other person gets the 3 of hearts? Does it matter if I talk about the 3 of hearts or the 4 of hearts? No. And it's coincidental that I'm wearing long sleeves today. All of these cards, each person has a 50-50 chance. 1/2 times 1/2 times 1/2 times 1/2 times 1/2. 1/2 to the 5th, and then I multiply by 2, because there's 2 ways. Either the first person gets all the 5 hearts, or the second person. When you do the multiplication out, you get 6.25%. So there are 8 choices here representing the possibilities of just none of them, 1 of them, 2 of them, 3 of them, 1 and 2, 1 and 3, 2 and 3, 1, 2 and 3. Without knowing any mathematics beyond elementary comparison, you should be able to eliminate a lot of these possibilities. If not, this course is not for you, and I will try to find a more appropriate class for you. But you should be able to eliminate a large number of these possibilities. Okay? So I am opening up the polling for voting. Okay? So vote A or the number 1 if you think none of these answers are correct. B if you think just 1, C just 2, D just 3, E 1 and 2, F 1 and 3, G 2 and 3, H 1, 2, and 3. Okay, so what do you think is the probability that 5 cards of the 26 are all in one hand? Okay, so only 9 people have voted, 10 people. Even the American electorate has a better rate than this. They may not be as accurate, but they have at least a better participation. All right, we're up to 23 votes. All right, 24, 25. We've got 14 seconds left. I don't know how to extend this. This is primitive technology. I can't extend the polls. You can't appeal and say I didn't understand that I had to vote today. No absentee ballots allowed. 3 seconds, 2 seconds, 1 second. All right, time is up. All right, so 3% said A, 18% said B, 7% said C, 11% said D, 55% said E and recognized something, although it's actually not as bad as I had feared. 0% said F, 0% said G, 3% said H. All right. These are the people who I think listen to Janet Jackson with wardrobe malfunctions. All right. It's possible you could maybe argue that 1 and 2 are different because I've put an approximation sign. So maybe they differ in the 8th decimal place. So I will not be so concerned that there are some people saying B, C, and as opposed to this. So I should really think that maybe we should combine B and C with E. Or maybe there really is a subtle difference. All right, that's one of the big problems right now. All right, some of them are flat out right. We're definitely not going to have 1, 2, and 3 all correct. And since 3 is significantly different from 1 and 2, that should kill this one. That should kill this one. OK. So for the most part, the answers are falling where you would expect. The correct answer is E. Yeah, we're a democracy. More people voted for E than anything else, so E is the correct answer. OK? What goes wrong here? So this is a really good argument. And one of the reasons I like this is we're talking about conditional probability today. This is a nice way to segue into conditional probability and look at a review of binomial coefficients, calculating when does order matter, when does order not matter. I have to form a hand of 13 cards, and I want to make sure 5 special cards are in a specific hand. I have 2 choose 1 ways of choosing who gets the 5 hearts. One person has to get all 5 hearts. That's 5 choose 5. Now for the other one, the next one, I have to assign the 13 cards to another person. And I want to look at what's going on for these hearts one at a time. So for each card, I'm trying to decide who gets it or not. And so what I'm doing is I'm looking at each card one at a time. And I'm saying, does it go to each person or not? And I'm saying here, and I don't want to get into too much detail right now because we only have so much time today, that the more cards you have already, the less chance you have of getting the next card. If I've already filled in one of your cards, you now only have 12 slots remaining for the next card. Then you have to ask the question of, is it OK to just change the order of the cards? Can I assume of my 26 cards, I put all 5 cards up in the top? Sure, as long as for each card, I give a chance for the card to go to either hand.
So just one thing that confused me about 2. So it's 13 over 26, right? Because there's 13 slots that one player has.
Yes.
26 slots in total. So you give them a card.
Yes.
And it's a heart.
Right.
And you give the other person a card. It has to not be a
I haven't given the other person a card yet. I'm dealing out the 5 hearts. For each card, I'm trying to say who gets it. And I'm looking at the cards one at a time. And I'm saying, once I give you the first heart, you now have one of your 13 positions filled. And now I'm looking at your next, you now have 12 positions remaining. And so I'm assuming each card is equally likely to go to any remaining space. So in some sense, I've put an order. Another way of looking at it, as soon as you have one heart in your hand, you have less of a chance of getting another heart because some of your hand has already been determined. Imagine I tell you 10 cards in your hand, and they're all non-hearts. Then you know you have no chance of getting all 5 hearts. The more information I give you about cards in your hand, the more you know about the probability of getting all 5 hearts. This is clearly a conditional probability exercise. The question is, what is the right way to formulate the conditional probability? But as soon as I start giving you information about the cards in your hand, that affects your probabilities for the subsequent events. Right now I'm saying I've given you the first card as a heart. Now I'm trying to decide who gets the next one. And the next card, it has to go equally likely into any of the 25 remaining spaces. Now the last one is I'm saying each card has a 50-50 chance of going to either person. That is correct. What's not correct is to say that all of these probabilities are independent. The more cards I give you, the less probability you start to have of other things. And so jumping a little bit ahead, in Chapter 6 we talk about the difference between how many and certain probabilities. So anybody know what one of my favorite bands of all time is? ABBA. Right? How many people are ABBA fans? How many people are, all right, I won't ask, how many people are secret closet ABBA fans? You can email me anonymously if you want. Okay? They were offered $250 million to get back together and tour. ABBA was two couples that got married and got divorced. And they reached the point in life when they had enough money and they really felt no need to get back together with people they did not want to be with. And they passed on $250 million. Okay? If you look at ABBA, so there's 4 people for ABBA, A, B, B, A. Because my Swedish is not so good, I will not actually try to write out their names. I'll just call it A1, A2, B1, and B2. We'll assume A1 and B1 were married and are now divorced. B2 and A2 are married and now divorced. How many ways can I choose 2 people from the 4?
4 choose 2.
4 choose 2. So there's 4 choose 2, or 6 ways to choose 2 from 4. Let's assume each person is equally likely to be chosen. All equally likely to be chosen, but won't be with their x. And unlike other parts in mathematics, we have to put an e in front of this x. Okay? How many pairs are there now? How many pairs are there now? 4. I can have A1 and B2. I can have A1 and A2. I can have B1. That's it. Okay. So I can have A1 and B2. I can have A1 and A2. I can have B1 and A2. And then the one I'm missing is B1 and B2. How often is B1 chosen? How many times is B1 in a pair? Half the time. How many times is B2 in a pair? Half the time. Each person is chosen half the time. So if you look at the probability have anyone is still 50%. But not all pairs are equally likely. So there's a huge difference between all pairs are equally likely and everybody's equally likely to be chosen. So you've got to be very careful when you're doing problems like this. Going back to what we were doing over here with trying to assign the cards. Each card is equally likely to be in either hand. But as soon as you know you have one card, that affects your probability of getting other cards. And if you go to the ridiculous extreme when you already have 13 cards in your hand, what's the probability you get the next card? It's 0. Your hand is full. Okay, so this is just one of many examples of conditional probability. Any questions on the mathematics of ABBA? It's not pivoting too well today. All right, we're all fine with mathematics of ABBA. Okay, so what I want to do now is I want to talk a little bit about conditional probabilities. So most events in life are conditional on other things, right? Can somebody give me an example of a conditional probability other than what we've just had on the board? Yes?
The temperature and what heavy winter coat.
Hopefully those are conditional. I actually had a friend in grad school whose wardrobe was constant no matter what the weather was outside. California casual. And so it did not matter how cold it was, he was always outside in shorts. But for most people, whether or not you wear a winter coat, the number of layers you wear will be a function of the temperature. Baseball game, the probability you win might be a function of who you have starting that game for you. And so, when you just say, what's the probability of winning? Well, I want to know who the starting pitcher is. I want to know, are you playing at home or on the road, maybe for football? A lot of events are conditional. If you know some information, you have additional information about what's going to happen. Imagine we roll 2 fair die. So roll 2 fair die, and let's say the tosses are independent. The first roll is a 3. What is the probability the sum is an 11? 0. Once my first roll is a 3, there's no way the sum can be large enough to get up to 11. That's going to be 0. Now, before I told you the first roll was a 3, what would you have said the probability of an 11 is? Before knowing first roll a 3, what would you have said? What would be the probability of an 11? 2 out of 36. And thank you so much for saying 2 out of 36 and not 1 out of 18. Don't reduce, don't simplify. Leave it as 2 over 36. That's far more illuminating as to what's going on. There are 2 out of 36 possibilities that would have given me a 11. Okay. What is the probability have a sum of 7 given a 3 on the first roll? 1 out of 6. So why is it 1 out of 6?
Well, because the only way to do that is to roll a 4.
The only way to do that is to roll a 4 on the second die. So 1 out of every 6 rolls of the second die will work. If I hadn't told you ahead of time that the first roll was a 3, what would it have been? So it would have been 6 out of 36 equals 1/6 if don't know the first roll. So I chose this event very carefully. I spent a lot of time working on this one. Why? What concept is this basically telling us? Independence. So in terms of the event of rolling a 7, that seems to be independent of what the first die is. It doesn't really matter what the first die is. You're always going to have a 1 in 6 chance of rolling a 7. For any of the other numbers, you will get some information based on the first roll. You can have some extreme cases, where the probability is now 0. But in general, knowing something about that first roll will affect your probabilities of subsequent events. In some situations, it will not matter. Okay? The probability of it being cold outside and me running out of M&Ms. Should those be independent events? Probably. We're not going to get to the level of, well, maybe it's so cold Professor Miller's car won't start, he can't get to the supermarket and buy more M&Ms. This did lead to a 2-hour delay for my kids' elementary school earlier this week because they were afraid it was too cold for the buses to start. You can carry things to ridiculous extremes, but for the most part, a lot of times it's not so bad to figure out when events are independent, when events are not independent. All right, so we want a good definition of conditional probability. So, conditional probability. So we write it as A, B. This is the probability of A given B. Okay? And so now when we're trying to find the probability of A given B, we want some kind of formula for this. So maybe we believe this is some function. And natural inputs to put in this function is maybe it should depend on the probability of A, it should depend on the probability of B. So this would be a nice guess. If the world were really simple, maybe the conditional probability is just a simple function of the probability of A and the probability of B. So we did this earlier when we were trying to find the probability of an intersection. We were trying to figure out, is there a nice formula? Can we sniff out what the answer should be before we do a long, detailed calculation? So in situations like this, you want to try looking at special cases. So let's try special cases. So good events is A equals B and A equals B complement. So if A equals B, what's the probability A happens given that B happens? If A equals B complement, so this was 1, if A equals B complement, what's the probability A happens given that B happens? 0. So we have two extreme cases. So if now the probability of A and the probability of B are the same, this only cares about those two numbers. So what would we want the probability of A and B to be in this case? Because now we have here the probability of A given B is 1. The probability of A given B is 0. We want the probability of A and the probability of B to be the same. What would be a good number for that? 1/2. Because if it's 1/2, I can't tell the difference between these two events. If B has probability 1/2, what's the probability of B complement? 1/2. So if now we take the probability of B equals 1/2 over here, and the probability of B equals 1/2 here, this would have to give us f of 1/2, 1/2 equals 1. And we would also have f of 1/2, 1/2 equals 0. So what this tells us is there can't be any simple formula that depends just on the probability of A and just on the probability of B. So in terms of trying to sniff out what the answer is, it has to be more complicated than this. Okay. Again, I could just jump to the definition of conditional probability. I could just jump to the expected counts approach. I want to try to give you a sense of how you would detect a formula. This is the more useful skill to get. This is the teaching you to fish skill. Okay? So if we tried something just depending on the probability of A and probability of B, we see by looking at special cases that there's no way this can work. What's wonderful is this eliminates every possibility for F. I don't even have to try to think of possibilities for F. It doesn't matter. Whatever F you give me cannot work. So this means the conditional probability has to be more than just the probability of A and the probability of B. We need something more. So now we should try and make our function even more complicated. So what else do you think it should depend on? So let's try the probability of A given B is now a function of the probability of A, the probability of B, and the probability of A intersect B. So I claim A intersect B is the next most natural thing to try. Right? So why would A intersect B be natural? Well, if I'm talking about the probability that A happens given that B happens, if you listen to it, both events have occurred. So I'm talking about A happens given that B happens. It seems reasonable that whatever answer I have has to depend on A intersect B. Because A intersect B is precisely the event that both A and B happen. So now I want to have some kind of answer that's going to depend on these three. And now I can start also looking at special cases. What if A equals B? What if A equals B complement? What if B is the entire space? And I can start going through this whole analysis. Question?
Isn't that just defining it by itself? You're saying that the probability of A intersect B is the exact event.
Right, but the probability that of A intersect B is not necessarily the probability of A given B. So for instance, in the example we had before when we were rolling the die, what's the probability we roll in 11? That had a positive probability, it was 2 out of 36. So there the probability of A intersect B would be 2 out of 36. But the probability that we roll in 11, given that our first roll is a 3, would be 0. So it would be some more involved thing. We can start looking at some special cases. The simplest, anybody know what the simplest example to take for B would be?
0.
we're not allowed to take 0. So if we took B to be an event that had 0 probability, what's the probability that A happens given that B happens? Oh, and by the way, B never happens. This is a situation where you say it's outside my pay grade. I am not allowed to discuss this. You know, what is the probability A happens given that B happens? So you want a situation that will never happen. Let's let B be the probability that, I don't know, Professor Miller roots for the Giants in the Super Bowl against the Patriots. Not going to happen. Any question you ask be predicated on Professor Miller rooting for the Giants in the Super Bowl over the Patriots. You cannot assign probabilities to that. These events are not in our realm of discourse. Okay? So if B has no chance of happening, it makes no sense to start assigning, well, what's the probability A happens given that B happens? Oh, and B never happens. It's not something worth talking about. So we always assume the probability of B is greater than 0. And if the probability of B is not greater than 0, it's just not worth discussing. So one of the extremes was try to say, well, let's say B is an event that doesn't happen. Well, that's not a good event to talk about. So what might be a good event to talk about? B always happens. So maybe B is the entire space. So if B equals omega, it should reduce to normal probabilities. So in this extreme case, we're talking about, given that something happens, what's the probability that A happens? Well, that's just the probability of A. So the answer needs to reduce, in the special case when B is omega, to the probability of A. So there's lots of different forms you can look at. It turns out the correct answer is the probability of A given B is the probability of A intersect B divided by the probability of B. And again, there's lots of different formulas. It turns out this is the one that works. I'm going to try to motivate this through both the expected counts approach and through a Venn diagram approach. So again, I unfortunately left Kayla's artwork. It's at home. I will try to be a good artist today. So here, this rectangle is omega. It is my entire world. Any Mask of Zorro fans here? Okay? So where Antonio Banderas is being told, until I say so, there is nothing beyond this circle. There's nothing beyond this rectangle. This rectangle is your entire world. This circle here is the A circle. This circle B, and this intersection here is the event A and B both happen. What does it mean to talk about the probability of A? That just means I want to know what's the probability I land in this circle over here. What about probability of B? That's the probability I land in this circle here. To talk about the probability of A given B, it means first I tell you B must happen. And now I want to know, given that B happens, what's the probability that A also happens? The way you should view this is as soon as I tell you B happens, you have to renormalize your world. And you throw away everything outside of B. Okay? And so as soon as I throw away everything outside of B, what probability should I assign to B happening now? In my mind, what should I be thinking the probability of B is? 1. So if the probability of B before was 0.8, I want in some sense bump it up to being 1. So I would divide by 0.8. If it was 0.6, I would divide by 0.6 to bump it up to 1. Now I look at the probability of A intersect B, and I inflate that by the same factor I inflated here. So if before this whole probability B was 0.8 and this was 0.2, I now inflate the probability of B by 0.8 to make this 1. I would inflate this by 0.8. And this is why what I'm really doing is I'm looking at the ratio. Inflating this is the same as dividing this by the probability that B happens. And so I'm renormalizing my world so that now I'm assigning probability of 1 to B happening. This is a very reasonable thing to do, because what am I doing? The probability that A happens given that B has happened. So in some sense, we've now reassigned probabilities so B has occurred. All right, so this is one of the two more popular ways of viewing what's going on. All right. Let me do the expected counts approach. And so the example in the book is I think we're going fishing, and I assume there's 1,000 fish. Could I have done the calculation without 1,000 fish? Could I have used another number? Yes. I like to just be a little bit extra cautious, just in case I've made any algebra mistakes, so that as I'm going through the calculations, at the end of the day, I don't have fractions. How many of you have taken a real analysis class? All right, how many of you know about a 3 epsilon proof versus an epsilon proof? So a lot of times in real analysis, you're supposed to show something is less than epsilon. And you often break something up into 3 different things, and you bound each one. And if you want to impress people, you make sure each piece is less than epsilon over 3, so that when you sum them at the end of the day, aha, it's less than epsilon. As you get older, you don't really care anymore. And you just, the first one's less than epsilon, the next one might be less than 5 epsilon, the fourth one might be less than 12 epsilon. It's going to sum to something less than a multiple of epsilon. Usually you're not that careless, and you'll make the first piece less than epsilon, the second piece less than epsilon, the third piece less than epsilon. The sum will be less than 3 epsilon. If you're trying to show something is arbitrarily small, if you show it's 3 times an arbitrarily small number, you've still shown it's arbitrarily small. It's just a question of how do you want to work the numbers. And so here, whenever I do these numbers, I could always assume that we are talking about 1 day rather than 1,000 days. And start talking about capturing half a fish or a quarter of a fish. To me, it doesn't really make as much sense. It doesn't flow as well to talk about catching half a fish. So that's why I just use big round numbers like 1,000. And rather than trying to do some of the math and figure out exactly what do I need, put in a bunch of 2s and 5s so that you don't have to worry about how things split. So what we're going to do is we're going to assume the following. So each day, 40% of the time you catch a trout, 25% of the time you catch a bass, 35% of the time you catch nothing, and only a trout. So we'll assume that as soon as you capture a fish, you are happy and you go home and you eat it. And you don't keep fishing until you catch a second one. So you either catch a fish or you don't. As a quick check, these probabilities do sum to 1. So it doesn't mean we haven't made a mistake, but at least it means we're potentially on the right track. Early in the class, we talked about trump splits with the 5-0. Well, instead of having a 5-0 trump split, what else could we have? Instead of having a 5-0, what else could we have? We could have 1-4, we could have 2-3. What you should do is you should calculate the probability of all of those trump splits and then add up all those probabilities. What should that all add up to? 1. And so if we're doing anything wrong, this might be a good way to check and see, is everything consistent? So you could take the 1/2 approach we used and see, is that consistent? All right, so imagine we have 1,000 days. How many days do we catch a trout? 400 days of trout. Sounds like a really bad HBO marathon. All right. How many days do we have the bass? 250 days of bass. And how many days of nothing? 350 days of nothing. So these are the days of catching a fish. So how many days do we catch a fish? 650 days catch a fish. So a natural question to ask is, what is the probability I catch a trout given that I've caught a fish? Well, I look and see, here is my 1,000 days, and I look and see what fraction of the days where a fish is caught have a trout caught. So probability catch trout given catch a fish is just going to be 400 over 650. And so this is a way to calculate conditional probabilities. What we want to do now is we want to take that expression and we want to write it in a better way. And so there are 2 algebraic techniques I love. Right? And the two algebraic techniques are multiplying by 1 and adding 0. This turns out to be a really good situation to multiply by 1. So we have the probability of a trout given we catch a fish. This is equal to 400 over 650. Okay? We can rewrite this as 400 over 1,000 divided by 650 over 1,000. Why would it be worth writing it like this?
I guess in your words, like in this example, that's maybe more illuminating because you're saying what's actually happening.
Yeah, this is describing what's actually happening. These are the probabilities we're given, right? We're given the probability we catch a fish is 0.65. So this is 0.65. This is 0.40. If we let B be the event where you catch a fish, and A the event that you catch a trout, what's the probability of B? That's 0.65. What's the probability of A? I'm sorry?
Oh, you're doing the conditional.
What's the probability we catch a trout? 0.4. Now, what's the probability of A intersect B? 0.4. So this is a little tricky. Are you surprised that the probability of A intersect B is the same as the probability of A? No. If you catch a trout, I'm not really giving you much information, or it's not really that restrictive to say, oh, also, I want to make sure you catch a fish as well. A trout is a fish. So when I write it like this, we can now see, oh, 0.4 over 0.65. So I chose this problem deliberately because it is very easy to get the wrong life lesson. When you're looking at this, one thing you might think the ratio is maybe it's the probability of A divided by the probability of B. Maybe that's the conditional probability. There's a lot of different things that could work in this case. It could be probability of A over probability of B. It's not. It's the probability of A intersect B over the probability of B. So when you have a small number of data points, it's very easy to be misled. All right? For those of you who have already seen the following, please do not speak up. This is one of my staples that I like to do. Since we're doing a lot of algebra, can somebody just help me out? What's 16 over 64? A quarter. I'm not quite sure why it's not pivoting today, so it's a quarter. 19 over 95. Fifth. 49 over 98. I'm sorry? Half. Let's do one more. 12 over 24. A half. 16 over 64, I cancel the 6's and I get 1/4. 19 over 95, I cancel the 9's, I get 1/5. 49 over 98, I cancel, I get 4/8. I have to do a little bit more work, I get to 1/2. The way you divide two two-digit numbers, if the opposite diagonals are equal, is you cancel the opposite diagonals. Therefore, 12 over 24 is 1/4. I will not grade your exams this way, don't worry. Okay? This is 3 data points that worked. Just because a formula has been verified for a couple of data points, does that mean I can use that formula? No, you can use stronger language than no if you'd like. Right? Are you beginning to get some confidence in the formula? Yes. I mean, you should start to get more and more confident the more times you see the formula working. If it's worked 3 times, I'm beginning to think maybe there's something there. Oh, nope, not at all. Yes?
Why did those 3 work?
Just coincidental. So it becomes an interesting question as to how many of these do you expect to work? Is there another one that I'm missing? What happens if I look at 3-digit numbers? Does it work the other way? There's lots of stuff you can do. I'm not going to get into too much detail about examples like this, but I want to leave you with a warning. I love experimental mathematics. So one of the things I'll be modifying the textbook tonight, and I'll be adding computer code to simulate dealing bridge hands and comparing and computing the probabilities and seeing which one is right for the probability of a 5-0 trump split. Whenever you have multiple ways of computing something, you want to write some code and get a sense of which answer do you think is right. I have talked to a lot of former Williams students who have told me off the record, also I can't say that because this is being recorded, that they no longer look at applications from people who can't code. It's extremely important. When you're in a situation where you're not sure what the right answer is, you want to be able to write a very simple computer code and experiment and say, well, which of these three are right, 1, 2, or 3? Are 1 and 2 the same? Do they differ in the 8th decimal place, or are they actually the same quantity? All right, so this was the expected counts approach. And so we end up with the following very nice formula. So we are left with the following. And we'll have to try to figure out why it's no longer swiveling. But all right. So conditional probability. If the probability that B happens is greater than 0, then the probability that A happens given B is the probability of A intersect B over the probability of B. As soon as you see the formula written like this, there should be a natural instinct. What do you want to do? Algebraically, what would you like to do to this equation? Get rid of the fraction. Why is this fraction bad? What are you not allowed to do in math unless you have extra special permission? Divide by 0. If you're in econ or physics, no problem. But here, in this part of the building, we are very worried whenever we might be dividing by 0. So rather than having an expression like this, why not look at the probability of A intersect B is the probability of A given B times the probability of B. And if you read it, this seems like a really good sentence. What's the probability that A and B both happen? Well, it's the probability that B happens times the probability that A happens given that B has happened. Well, as soon as we have this, we can now do a symmetric argument. What is the probability that B and A happen compared to the probability that A and B happen? They're the same. I've just flipped the roles of A and B. So this now becomes the probability of B given A times the probability of A. So these two expressions are equal. So we can solve for one in terms of the other. So we can get the probability that A happens given B is the probability that B happens given A times the probability, let me make sure I'm doing this right, of A divided by the probability of B. And so what result is this? Bayes' rule. So here's Bayes' rule. It just follows from the definition of conditional probability. The whole reason this is useful is sometimes one piece of information is more useful or more accessible than another. And you might be in a situation where I know the probability that B happens given A, but I want to know the probability A happens given B. Okay? So this is Bayes' rule. It allows you to pass from probability of one type of events to another type of events. If you go on in statistics, this is one of the major themes in statistics, is exploring consequences of this relationship. Okay, so again, the more you know about some events, the more probabilities you can calculate. Some probabilities are easier to calculate than others. I'm not going to go through the medical example. It's written up in the book where you have a test, you have a certain probability that the test comes back positive when you have the disease, and the false positives, false negatives. And you can use this to figure out if you test positive for a rare disease, should you panic? And the answer for the most part is no. You should be a little concerned. It's not, of course, good news to be testing positive for a bad disease. But if these diseases are really rare, you're actually more likely to have a false positive than to actually have the rare disease. What do you think you should do? No, get tested again, get a better test, get a more expensive test. Okay? So you can often use this as a quick way. The more expensive test, there's very natural reasons why you would not want to give the more expensive test to everyone. But for somebody who tests positive, that would probably be a really good candidate for a second test. So the book goes through in great detail what's the probability if you test positive you have a given disease. And one of the big ideas or themes used in calculations like this, no, it's not, we'll have to fix this later, is trying to use what's called a partition for events. And so when you look at a partition, bless you, this should be very similar to things you've seen before. One of the things we always do is we try to break things up into cases. And the cases are supposed to be mutually exclusive, and they're supposed to be exhaustive. So everything falls into one case and only one case. Sometimes when you're proving things, your cases are not mutually exclusive. Sometimes things fall into multiple cases. That's okay. You're just trying to prove something is true. As long as you exhaust all possibilities, that's fine. For a partition, we want the sets in the partition, the events in the partition, to be mutually disjoint. You can't be in multiple things. So if you're being partitioned, you're into one and only one thing. That's a little bit different than proving by cases. It's similar in that you're splitting things up. So for partitions, imagine you have something like this, and here would be a partition. Maybe this is B1, B2, B3, B4, B5, B6. And I would have partitioned my space into 6 smaller spaces. So we say a set BI is a partition of omega if 1, it's at most countable, 2, the union is omega, and 3, they're pairwise disjoint. So if you partition the space, you can be in one and only one BI, and in fact you're in exactly one BI. So another way of saying that is each x in omega is in exactly one BI. And so the question is, why do we care about partitions? What is the advantage of using partitions to tackle probability problems? Well, we can actually use partitions to calculate probabilities. And so when you do the analysis of the probability that you have this deadly disease given that you've tested positive, one of the key ingredients is doing a partition. So if I want to know what's the probability that A happens, this is the same as the probability that A and B happen plus the probability of A and B complement happen. So this is the simplest possible partition. So maybe here's B complement, and here's A. If I want to know what's the probability A happens, well, I can split A up into 2 disjoint sets. And so what I'm doing is I'm writing A as A intersect B union A intersect B complement. And this is now going back to all of our set theory stuff from earlier in the semester. I'm splitting the set A into 2 disjoint sets. Well, because these sets are disjoint, what's the probability of a disjoint union? It's the sum of the probabilities. If instead of having 2 sets B and B complement, if I had 3 sets, it would be the probability of A intersect B1 plus the probability of A intersect B2 plus the probability of A intersect B3. And so in general, you get the probability of A is the sum of the probability of A intersect BI. I goes from 1 to infinity. We can expand on the probability of A intersect BI. We can use the conditional probabilities for that. This is the same as the sum, I goes from 1 to infinity, of the probability of A given BI times the probability of BI. So again, it all comes down to how do people give you information. And if you think back about what we were doing at the start of class, with the cards, there are conditional probabilities going on here, and the probability you get cards at certain times is going to depend on what cards you already have in your hand. Certain calculations, certain probabilities are easier than others. All right, so this is a good place to stop. I will send you an email as to what else there is to do from Chapter 4. Basically, it's independence. So we will finish up independence next time, and then we will go through Chapter 5 and Chapter 6. If there's particular material from them that you want to see, email me.